君の虜になってしまえばきっとこの夏は充実するのもっともう戻れなくたって忘れないで
For our fourth topic, we have the water pollution in lakes. Under this, we have the certification and turnover, biological zones, lake productivity, eutrophication, algal growth requirements, the limiting nutrient, control of phosphorus in lakes, and the acidification of lakes. Phosphorus dominates other pollutants in controlling water quality in the vast majority of lakes, that we will give it a special emphasis. A knowledge of lake system is essential to an understanding of the role of phosphorus in the lake pollution. Limnology is the study of lake. So let's start. Stratification and turnover. Nearly all lakes in the temperate climate zone become stratified during the summer and overturn or turn over in the fall due to the changes in the water temperature that result from the annual cycle of air temperature changes. Lakes in cold climate undergo winter stratification and spring overturn. Nonetheless, they do help determine the water quality.
Stratification of lake during summer and winter. During the summer, the surface of the lake is heated both indirectly by contact with warm air and directly by sunlight. Warm water, being less dense than cool water, remains near the surface until mixed downward by turbulence from wind, waves, both and other forces. Because the turbulence extends only a limited distance below the water surface, this results to the upper layer of well-mixed warm water, which is called epilimnion, floating on the lower water, which is called the hypolimnion, which is poorly mixed and cool as shown in our first figure. Because of good mixing, the epilimnium will be aerobic or will have a DO. The hypolimnium will have a lower DO and may become anaerobic or devoid of oxygen. The boundary here is called the thermocline because of the sharp temperature change and therefore density change that occurs within a relatively short distance. The thermocline may be defined as a change in temperature with depth that is greater than 1 degree Celsius per meter. You may have experienced a thermocline while swimming in a small lake. As long as you swim horizontally, the water is warm, but as soon as you tread water or dive, the water turns cool. You have penetrated the thermocline. The depth of the epilimnion is related to the size of the lake. It is as little as 1 meter in small lakes and as much as 20 meters or more in larger lakes. The depth of the epilimnion is also related to the storm activity in the spring when stratification is developing. A major storm at the right time will mix warm water to the substantial depth and thus create a deeper than normal epilimnion. Once formed, lake stratification is very stable. It can be broken only by exceeding violent storms. In fact, as the summer progresses, the stability increases because the epilimnion continues to warm, while the hypolimnion remains at a fairly constant temperature. In fall, as temperature drops, the epilimnion cools until it is more dense than hypolimnion. The surface water then sinks, causing overturning. The water of the epilimnion rises to the surface where it cools and again sinks. The lake thus becomes completely mixed. If the lake is in a cold climate, this process stops when the temperature reaches 4 degrees Celsius, since it is the temperature at which water is most dense. Further cooling or freezing of the surface water results in winter stratification, as shown our second figure. As the water warms in the spring, it again overturns and becomes completely mixed. Thus, temperature climate lakes have at least 1, if not 2, cycles of stratification and turnover every year.
Now we're here to the biological zone. Lakes contain several distinct zones of biological activity, largely determined by the availability of light and oxygen. Most important zones includes euphotic zone, littoral zone, and benthic zone. So down here, you can see the biological zones in a lake and where it is located. Let's start with the euphotic zone. So what it is? It's the upper layer of water through which the sunlight can penetrate. All plants grow and occur in this zone. The depth of the euphotic zone is determined by the amount of turbidity blocking sunlight penetration. In the euphotic zone, plants produce more oxygen by photosynthesis than they remove by respiration. Below the euphotic zone lies the profundal zone. The transition between the two zones is called the light compensation level. The light compensation level corresponds roughly to the depth at which the light intensity is about 1% of unattenuated sunlight. It is important to note that the bottom of the euphotic zone only rarely coincide with the thermocline. For a second zone, we have the littoral zone. Littoral zone. Yeah, the shallow water near the shore in which rooted water plant can grow. The extent of the littoral zone depends on the slope of the lake bottom and the depth of the euphotic zone. The littoral zone cannot extend deeper than the euphotic zone. Third zone, the benthic zone. It is the bottom sediments comprise the benthic zone. An organism living in the overlying water die. These settle to the bottom where they are decomposed by organisms living in the benthic zone. Bacteria is always present here. The presence of higher life forms such as worms, insect, and crustacean depends on the availability of oxygen. Lake productivity. The productivity of a lake is a measure of its ability to support food web. A lake's productivity may be determined by measuring the amount of algal growth that can be supported by the available nutrients. Although a more productive lake usually will have a higher fish population, the number of the most desirable fish may decline. Increased productivity generally results in reduced water quality because of the undesirable changes that occurs as the algal growth increases. Because of the important role productivity plays in determining water quality, it forms a basis for classifying lakes. So we have here the oligotrophic lakes. Oligotrophic lakes have a low level of productivity due to a severely limited supply of nutrients to support algal growth. Water is clear enough that the bottom can be seen at a considerable depth. In this case, the euphotic zone often extends into the hypolimnion, which is aerobic. Oligotrophic lakes therefore supports cold water game fish. Lake Tahoe on the California-Nevada border is a classic example of an oligotrophic lake. Eutrophic lakes. Eutrophic lakes have a high productivity because of an abundant supply of algal nutrients, and it's highly turbid. The algae cause the water to be highly turbid, so the euphotic zone may extend only partially into the epilimnion. As the algal die, they settle to the lake bottom where they are decomposed by the benthic organisms. Eutrophic lake supports only warm water fish. In fact, most cold water fish are driven out of the lake long before the hypolimnion becomes the anaerobic, because they generally require dissolved oxygen level at least 5 mg per liter. Highly eutrophic lakes may also have large mats of floating algae that typically impact unpleasant taste and odor of the water. Number 3, the mesotrophic lakes. Lakes which are intermediate between oligotrophic and eutrophic lakes are called mesotrophic. Although substantial depletion of oxygen may have occurred in the hypolimnion, it remains aerobic. Fourth is the senescent lakes. These are very old, shallow lakes that have thick organic sediments and rooted plants or water plants in great abundance. These lakes will eventually become marshes. Eutrophication. Eutrophication is a natural process in which lakes gradually become shallower and more productive through the introduction and cycling of nutrients. Thus, oligotrophic lakes gradually pass through the mesotrophic, eutrophic, and senescent stages, and eventually filling completely. The time for this process to occur depends on the original size of the lake and on the rate at which sediments and nutrients are introduced. Cultural eutrophication. It is caused when human activity speeds the processes naturally occurring by increasing the rate at which sediments and nutrients are added to the lake. Thus, lake pollution can be seen as the intensification of the natural process. Water quality management in lakes is primarily concerned with the slowing eutrophication to at least the natural rate. To understand the factors involved in eutrophication, it is necessary for us to understand the factors contributing to the algal growth. Algal growth requirements. To grow, all algae requires macronutrients such as carbon, nitrogen, and phosphorus. They also need micronutrients such as trace elements. Lack of any one nutrient will limit the total algal population. Carbon. Algae obtain their carbon from carbon dioxide dissolved in water. As carbon dioxide is removed from the water, it is replenished from the atmosphere. The atmosphere is, of course, a virtually inexhausted source of this gas. When algae are either consumed by higher organisms or die and decompose, the organic carbon is oxidized back to carbon dioxide, which returns either to the water or to the atmosphere to complete the carbon cycle. Nitrogen. Nitrogen in lakes is usually in the form of nitrate and comes from external sources by way of infloating streams or groundwater. When taken up for algal growth, the nitrogen is chemically reduced to amino nitrogen and incorporated into organic compounds. When dead algae undergo decomposition, nitrogen cycles from nitrate to organic nitrogen to ammonia and back to nitrate as long as the water remains aerobic. Denitrification. Denitrification reduces the average time nitrogen remains in the lake system. Some photosynthetic microorganisms can also fix nitrogen gas from the atmosphere by converting it to the organic nitrogen. Cyanobacteria. A photosynthetic bacteria and the most important nitrogen-fixing microorganism. Formerly, it is known as the blue-green algae. Generally undesirable because it forms slightly floating mats, it has a unpleasant odor and smell, and it produces toxins which kill fish. Not prevalent unless the supply of soluble fixed nitrogen is reduced to low level. Phosphorus. Phosphorus in lake originate from external sources and it's taken up by algae in an organic form of PO3/4 and incorporated into organic compounds. During algal decomposition, phosphorus is returned to the inorganic form. So what happened to the phosphorus? It transferred into the sediments. Some of it is undecomposed organic matter. Some of it precipitates into iron, aluminum, and calcium, some bound to clay particles. To a large extent, the permanent removal of phosphorus from the overlying water to the sediments depends on the amount of iron, aluminum, calcium, and clay entering the lake along with the phosphorus. Trace elements. The quantities of trace elements required to support algal growth are so small that most fresh water have sufficient amount for a substantial algal population. The limiting nutrients. Liebig's law of the minimum states that growth of a plant is dependent on the amount of foodstuff that is presented to it in a minimum quantity. As applied to algae, it means that algal growth will be limited by the nutrient that is least available. Of all the nutrients, only the phosphorus is not readily available from the atmosphere or the natural water supply. For this reason, phosphorus is deemed the limiting nutrients in lakes. The amount of phosphorus controls the quantity of algal growth and therefore the productivity of lakes. Control phosphorus in lakes. Because phosphorus is usually the limiting nutrients, control of cultural eutrophication must be accomplished by reducing the input of phosphorus to the lake. Other strategies for revising and slowing the eutrophication process includes precipitating phosphorus with additions of aluminum or removing phosphorus rich sediments by dredging. To be able to reduce phosphorus inputs, it is necessary to know the source of phosphorus and the potential for their reduction. The natural source of phosphorus is the weathering of the rock. It is exceedingly difficult to reduce the natural inputs of phosphorus. If these sources are large, the lake is generally naturally eutrophic. For many lakes, the principal sources of phosphorus are the result of human activities. Most important sources include municipal and industrial wastewater sewage from septic tanks, and also agricultural runoff that carries phosphorus fertilizer into the water. Municipal and industrial wastewater. All municipal sewage contains phosphorus from human excrement. Many industrial wastes are high in this nutrient. In this case, the only effective way of reducing phosphorus is through advanced wastewater treatment processes, which are discussed in Chapter 6, which is the previous chapter. Municipal wastewater also contain large quantities of phosphorus from detergent containing polyphosphate, which is a chain of phosphate ions, usually three linked together. Septic tank sewage. Septic tank sewage. As treated wastewater moves through the solid towards the lake, phosphorus is absorbed by soil particles, especially clay. Thus, during the early life of the tile field, very little phosphorus gets to the lake. However, with time, the capacity of the soil to absorb phosphorus is exceeded, and any additional phosphorus will pass on into the lakes, contributing to the eutrophication. The time it takes for phosphorus to break through the lake depends on, first, the type of soil, second, the distance to the lake, third is the amount of wastewater generated, and the fourth is the concentration of phosphorus in the wastewater. Ways to prevent phosphorus from reaching the lake. First is to put the tile field far enough from the lake that the absorption capacity of the soil is not exceeded. Second is to replace the septic tank and the tile field with a sewer to collect the wastewater and transport it to the treatment facilities. Agricultural runoff. As rainwater washes off fertilizer field, some of the phosphorus is carried into the streams and into the lakes. Most of the phosphorus not taken up by growing plants is bound to soil particles. Bound phosphorus is carried into the streams and lake through soil erosion. Waste minimization can be applied to control the phosphorus loading to the lakes from agricultural fertilization by encouraging farmers to fertilize more often with smaller amounts and to take effective action to stop soil erosion. Acidification of lakes. Pure rainwater has carbon dioxide dissolved in water to form carbonic acid. The pH level of this is approximately 5.6, while acid rain has a pH level of less than 5.6. Many fish are very sensitive to low pH level. Example of this is trout and Atlantic salmon. When the pH level becomes less than 5.5, most are severely stressed and only few will survive. When the pH level becomes less than 4, cricket, frog, and spring pepper experience mortalities in excess 85%. Other factors that affect the susceptibility of lake to acidification are: first, the permeability. Second is the depth of the soil. Third is the bedrock. Fourth is the slope and size of the watershed. And fifth is the type of vegetation. Our fifth topic is water pollution and estuaries. We have here the definition of estuary and the example of it. Estuary, formed along the coastline where fresh water from rivers and streams flows into the ocean. It is a place of transition where fresh water mixes with the salt water. Estuaries are influenced by tide. Example of estuaries are Bay of Fundy, Florida Bay, Mobile Bay, and a lot more. Estuaries ecosystem is extremely complex. Numerous habitats support an abundance of wide variety of different animals. Estuaries are subject to a plethora of pollutants. The management of the water quality is complicated by the number of political jurisdictions that touch on the estuaries as well as competing needs of the organism that's living here. Competing with the environmental value is the economic value of estuary to commerce. Our sixth topic is the groundwater pollution. Under this, we have the uncontrolled releases and the saltwater intrusion. Groundwater has a large protection from contaminants, but once contaminated, it's already difficult to return to a prestige stage. Two major sources of contaminants is first uncontrolled releases of chemical and biological contaminants. Second is the saltwater intrusion from overpumping of wells. So let's start with uncontrolled releases. Sources. Discharge from improper operated or located septic tank system. Leaking underground storage tanks. Improper disposal of hazardous and other chemical waste. Spills from pipeline or transportation accident. Recharge of groundwater with contaminated surface water. Leaking landfills and leaking retention ponds or lagoons. The properties of contaminants in the aquifer material govern their migration of the contaminants. Water-soluble chemicals are likely to move vertically down through the soil to aquifer and migrate with the water. Example of water-soluble chemicals are nitrate, methyl tertiary butyl ketone or a gasoline additive, and also methamidophos, which is a pesticide. Non-aqueous phase liquids, or NaPLS. Chemicals that are only sparingly soluble migrate through the aquifer as separate non-aqueous phase. It has two categories based on their density. First one is the light NaPLS, or the light non-aqueous phase liquids. They are less dense than water and tend to float on the water table. Second one is the dense NaPLS, or what we call the dense non-aqueous phase liquids. It have higher density than water and will tend to sink on the aquifer until they reach the impervious barrier. Saltwater intrusion. Freshwater aquifers near oceans and above saline aquifers may become contaminated with salt water when water is pumped from wells that draw water that is too close to the freshwater-saltwater interface. Now you can see the figure of the freshwater-saltwater interface in coastal aquifers draining into ocean. Because seawater is heavier than freshwater, it will form a saltwater wedge in aquifers that drain into the ocean, as you can see on the figure. Using the notation in the figure and assuming that the freshwater moves horizontally to the ocean and that the interface is abrupt and that it occurs on the shoreline, we can express the freshwater pressure at any point of the interface as PF, or the freshwater pressure, is equal to H, the height of the water table above sea level, plus the Z, the distance of interface below sea level, times the PF, the density of fresh water. For solving the Z, as we know, Z is the distance of interface below sea level. Z is equal to PF, the density of fresh water, over PS, the density of salt water, minus PF, the density of fresh water, times H. As we know, H is the height of the water table above sea level. Taking the density of fresh water as 1 grams per ml, and that the seawater as 1.025 grams per ml, we can use this expression to estimate that for coastal waters, Z is approximately 40 H. Thus, for every meter that the water table is above sea level, there will be 40 meters of fresh water before salt water is encountered. As you can see on our next figure is the geometry and symbols for upcunning of salt water beneath a pump well. Dashed lines represent static position of water table and interface. When fresh groundwater is underlain by saline water, pumping a well in the fresh water will cause the interface to rise below the well. as shown in our figure. This upcurrent is in response to the pressure reduction on the interface that results from the drawdown of the water table around the well. If the well screen is close to the saline water or pump rate is too high, salt water may be drawn into the well. The height of the upcurrent below the center of a well after an infinite pumping time of the fresh water well may be estimated by using the Beer-Indaga 1968 equation as modified by Smorek and Mercado in 1969. The equation is Z infinite is equal to Pf times Q over 2 pi times the quantity of Ps minus Pf times K times L, where Z infinite is the rise of the concenter at T is equal to infinite, Q is the well discharge, K is the hydraulics conductivity, and L is the depth of freshwater-saltwater interface below well bottom prior to the pumping.